Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Welcome to Pytorch tutorial. Today's topic is simple classification task using neural networks. Today we'll build our very first neural network. So focus on the structures of the neural networks because that would be necessary in future videos as well. To build a neural network in Pytorch, we will import Pytorch, Torch, Torch Vision, Torch.nn, TorchVision.transforms, TorchVision.dataset, of course variable from torch.autograd, and we'll import time package of Python to keep track of how much time it's taking to run one epoch. Once you have imported all the modules and packages, next thing is to download the dataset. We are downloading Fashion MNIST dataset I talked about in a previous video. I'm putting my dataset in my_data folder, which will appear here. Once the download is done, you will see that there is a folder called my data in this span. Next thing is to choose how many batches do you want to load the datasets in and how much epoch do you want to run. I have kept the number of epochs as 10 and batch size is 100. So what does it mean? It means that although you have 60,000 images for training dataset and 10,000 images for test dataset, at one time only 100 images will be loaded to the main memory of the computer. To do that, you have to use torch.utilsdata.loader and then give it the name of the training dataset. Here I have downloaded the data as train set and test set. So train loader will have the train dataset and it will load 100 images at one time. So inside this function, you have to pass train set, the name of the training dataset, then batch size equals to the batch size number that you have decided. You can make it 200, 300. Sometimes we prefer giving it a size of 128 or 256. So you can choose anything you want. I have chosen 100 to make all the batch sizes equal. Shuffle equals to true will shuffle the datasets, the data points or images in this case in the training and test dataset, and number of workers means how many threads will work to load the data. So once we run it, we'll get our train loader and test loader. This is a very useful tool in Pytorch. Next thing is how many training images are there and how many test images are there. Like I said earlier, our training set has 60,000 training images and our test set has 10,000 test images. But when you create train loader, you have batches of 100 images. So what do you think the number of batches there in the train loader? It should be 60,000 divided by 100, right? Because each batch is of length 100 images and there are 60,000 images. So if your answer is 600, you are correct. Same goes for the test loader. There are 10,000 images in test set and each batch is of size 100. So the test loader has a total of 100 batches. The length of test loader is 100. So just to give you an idea of how the dataset look like, I'm using NumPy and I'm converting our train set data into a NumPy variable so that we can iterate over it and we can plot it using Matplotlib. So the first image is of a shoe. The second image is of a t-shirt. Okay, let's build our very first neural network. I have chosen the name simple_MLP. As I've mentioned in the previous videos in Pytorch, if you are building a neural network model, you have to use object-oriented programming language like Python. So you have to use class, and inside it you have to define your methods. So MLP stands for multi-layer perceptron. So a fully connected simple neural network is called MLP, that is multi-layer perceptron. Inside the multi-layer perceptron, I'm creating a constructor class, which is super and calling itself. This is called a constructor class. And I have a size list. Here you can see when I call the function, I pass a list that is 784, 110. What does it signify? 784 is the resolution of the image. When I flatten it, that is 28 by 28. If you multiply 28 with 28, you will get 784. I have 100 images in per batch, and I have 10 classifications. So layer size gives you how many layers I want in my multi-layer perceptron. Size list is the size, as in this case it's 3. So I'm creating one linear layer and then I'm passing it through a ReLU layer. ReLU stands for rectified linear unit. It's an activation function. I'll talk about activation functions in a later video and also about the optimizers. And then I'm appending it into another linear layer and finally a sequential layer that combines all of them. Just be careful about the resolution or the shape of the layers. The first linear layer has a dimension of 784 by 100. The second linear layer has a dimension of 100 by 10. That's how you create linear layers in multi-layer perceptron 0, 1, 1, 2. So that the first layer has input as 784 and it outputs 100, and in the second layer your input size is 100 and output size is 10. Output size is 10 because I have 10 classes. So my goal is to output 10 probabilities, and I'll take the maximum of all these probabilities and I'll check which class does it belong to. Next, I pass 784, 110, and I'm creating a criterion as my loss function, which is cross entropy loss, which is a very good loss function for classification tasks. My learning rate is 0.001, and my optimizer is Adam. I'll talk about Adam optimizer in a later video. Adam stands for adaptive momentum. It is much better and faster than stochastic gradient descent. I have CUDA available. I have checked it. Then I define my training class, my testing class, training method and testing method. And then I run my neural network, and it will take some time to run this. So meanwhile, I'll tell you about my training and test methods. So in train method, that is train underscore epoch, I'm calling my model, which was built or instantiated on simple underscore MLP. the train loader, the optimizer, and the criterion. So in this case, I'm calling optimizer.0_grad to initialize the gradients after each epoch. The data is loaded to device that comes from train loader. The target, that is the label, is loaded to device as long as I mentioned in the previous video. Outputs are fetched from implementing model on top of the data. These are the predicted targets, and I calculated loss on the predicted targets and actual targets. I calculated loss. The loss dot backward is basically doing a backward propagation, and optimizer dot step is initializing all the weights and biases in each epoch. Then I print the training loss and I create how much time it took to run, and finally I'm returning the running loss in the training dataset. For the testing, I'm doing almost the same thing. Model.evaluation prepares the model for testing. I have running loss, I have total prediction, how much prediction I got correct, and finally I'm calling the data and target from the test loader. Once I'm done with that, I am loading my data and target to device, that is my GPU, and calculating outputs. Those are my predicted outputs. And just like previous video in logistic regression, I'm getting the predicted value as in which class has the maximum probability, and I'm calculating my efficiency of the network or accuracy of the network. So, and finally, I'm returning the running loss and accuracy. And this is how it looks like. Once you are done with this, you will get a training loss, how much time it took, a testing loss, and the testing accuracy. You can see that the test accuracy increases with time, and our final test accuracy after 10 epochs is 87.79. If you run more epochs, you will get better accuracy, that is for sure. Finally, I create a plot just to check whether the training loss are decreasing with time and testing loss are decreasing with time, which is perfect. So I'm going on the right track, and my model is good. Of course, the training loss will have a sharper decrease in loss in most cases, and training loss will have a shallow decrease in loss with each epoch, but the accuracy should increase with each epoch, which is my case, so I'm good. Thank you.